Okay, continue with the last lecture that we left uh, in the signal propagation part and channel modeling. These are some of the popular large-scale propagation models. Include free space model, two-ray model, Okumura model, and Hota model. Free space model power is directly proportional to 1 over d square, or you can say inversely proportional to distance, whereas two-ray model has indirect relation with distance -4. So let's first discuss free space propagation model. So this model is used to predict receive signal strength when the transmitter and receiver have a clear, unobstructed line of sight path between them. Now there is difference between line of sight path and line of sight communication. So we use this line of sight path and line of sight communication in different ways. So when we say line of sight communication, that means that is from transmitter to receiver communication. In that, the transmitter and receiver should be facing each other. Like in microwave communication, the two microwaves, transmitting microwave as well as the receiving microwave, or vice versa, should be facing each other, and they should be coordinated, or their coordinates set in such a way that they should be on the same line. So that kind of communication is called line of sight communication. Typically a base station to mobile station or vice versa, that type of communication is non-line of sight communication. However, the path between the base station antenna and the mobile station can be line of sight path or non-line of sight path. So that is path, it's not communication. So line of sight path and line of sight communication have totally different meanings. Okay, is it clear? So here we are saying that this model is used to predict receive signal strength when the transmitter and receiver have a clear unobstructed line of sight path between them. That is means between transmitter and receiver. In that case, it can be any mobile station, whether can be transmitter or the base station or vice versa. So it obeys the power law. Then the received power at a distance d will be equal to Pt, that is the transmitting power, Gt, that is the transmitting antenna gain, receiving antenna gain, lambda square, the frequency that we are using, it's lambda, and 4 pi whole square d square, and L. L is the system loss factor, not related to propagation. So this is the received power that is equal to this expression 1, where I already told you what is Pt and Gt. D is the TR separation in meters, and L is the system loss factor, and lambda is equal to wavelength in meters. So the gain of antenna is related to its effective aperture, that is AE. So you can calculate gain from here, that is 4 pi AE by lambda square. If we know that what is the effective aperture area, that is AE, we can calculate the gain using this expression 2, that is 4 pi AE by lambda square. So effective aperture area basically related to the physical size of the antenna and the wavelength. And wavelength is given by lambda is equal to c by f, or you can put in radians per second by putting 2 pi c over wc. So if you put here 2 pi f, so this becomes wc, and you need to put an extra 2 pi in the numerator because you have put 2 pi in the denominator. So the equation will change from c over f to 2 pi c over w omega c, where omega is the radian per second and c is the speed of light. Instead of hertz per second, if you want to calculate that in radian per second. Whereas L can be greater than or equal to 1 is due to transmission line attenuation, filter losses and antenna losses. So L basically covers the losses done through the transmission due to attenuation. Filters use their losses and antenna losses. So equation 1 shows that received power decays with distance at a rate 20 dB per decade. So if you convert this into the logarithm form, you can see that received power is indirectly proportional to d square. So if you convert this into the logarithm scale, this 2 will multiply, that will become 20 log of d. So that says that 20 dB per decade. So this 20 dB comes from there. So antenna gains are normally specified in units of dBi. That is dB gain with respect to an isotropic antenna, or dBd. That is dB gain with respect to a half wave dipole. So if it is dBd, that is half dipole. If it is I, then it is isotropic antenna. Path loss is defined as the difference in decibel between the effective transmitted power and the received power. So that is the definition of path loss. So free space propagation model basically help us in calculating the received power at a distance. So if you know the transmitting power, you can calculate the received power from the using the free space propagation model. Then you can calculate the path loss very easily, because it's a difference in dB between the transmitting power and the received power. So PL here is power loss in dB is equal to 10 log PT over PR. If you convert that into the logarithm scale, it will be 10 log PT minus PR, or in conventional form it will be equal to minus 10 log GT GR lambda square by 4, minus because it's a loss. So to determine loss, we have put here, and from the equation 1 you can calculate PT over PR from here. See, so from equation 1 we can evaluate the PT over PR in equation 4. After that, equation 4 will become this 10 log GT GR lambda square 4 pi square D square. And if antenna gains are excluded, if we say that GT and GR are equal to 1, then this equation will become minus 10 log lambda square by 4 pi square and D square. So this model is valid prediction of received power for values of D in the far field of a transmitting antenna. Means there should be some distance between the transmitter and antenna, where you are calculating the power that should be far field of a transmitting antenna. The far field region is defined as the region beyond far field distance D of F, which is given by. So what is the far field distance? Then you can also calculate with the this formula of equation 6, that is 2d square by lambda, where d is the largest physical linear dimension of the antenna. So again, this factor, far field distance factor, depend on the physical antenna dimensions. So here you have to take the largest physical linear dimension and you divide it by the lambda, d square of the largest physical linear dimension. Additionally, DF must fulfill the following criteria. It should be greater than D, and DF should also be greater than lambda. So from one it is clear that DF must not be 0. A kilos in distance D naught that is greater than or equal to D of F can be used to measure or predict the reference signal power. If you know the power up to a point D naught, then you can calculate the further power by referencing that power at that distance. Then the received signal power at any distance greater than D naught can be predicted as follows. So D is the distance where you want to calculate the received power, and D naught is the distance up to that point. You know what is the receive power up to that distance. Then using D naught you can calculate the reference power at the distance D using the then you can calculate the receive power at distance D using the reference power at the D naught. We often express signal power in dBm or dBW. So receive power in dBm is equal to 10 log receive power divided by 0.001 watt plus 20 log over D naught and over D. If you convert this formula, that is receive power in normal receive power, if you want to convert that in dBm, then you have to use this expression 10 to do that, where PR D naught is in units of watts. The reference distance D naught for practical system using low gain antenna in the 1-2 GHz region is typically chosen as 1 meter indoor and 100 meter to 1000 meter outdoor. So we do use this D naught to calculate the receive power at a distance D, and these are the typical values of frequencies from 1 to 2 GHz chosen as 1 meter. So D naught can be equal to 1 meter indoor and can be 100 meter to 1000 meter outdoor if the frequency ranges from 1 to 2 GHz. So then next we have practical link budget design using path loss models. So most radio propagation models are derived from analytical and empirical methods. So analytical are the ones that have some mathematical expressions. You put some values and drive the values, whereas empirical methods are the ones in that trials or the experiments took place, and from there whatever data we get, we say and we formulate a formula or something that we call that the empirical approach or method. So empirical approach involves curve fitting or analytical expressions to recreate a set of measured data. So in empirical method, we basically calculate or measure the not calculate, but we measure the data. Using that measured data, we can make analytical expression. Then we can calculate the data from using that analytical expression that has been resulted from the empirical approach. Propagation factors, known and unknown, are taken into account. So that is the advantage of having the link budget using loss models. Disadvantage may not be valid for environment other than the measured one. So some classical propagation models are discussed below. So this link budget are the path loss models, are the free space propagation model, and the other models help us to calculate the receive power. So basically, it's like that we are transmitting some power. Let's suppose P of t, and we know that the distance between the transmitter and receiver is d. Then at distance d, what will be the power? What will be the power received by the received antenna? So why it is important to know that what power does the user is receiving? Why we bother for that? Because there is a minimum power that should be received by the receiver antenna in order to decode the signal properly. If the received power is less than that threshold power or the minimum power that is required by the receiver antenna to receive the signal with that power to further process the signal, if received signal is less than that power, then your system or the receiver antenna and the other things will not be able to process the signal because they are not receiving the signal with that minimum power that is required by the receiving antenna. So it is very necessary that we should link budget the model or link budget the channel in between transmitter and receiver before deploying it in the real environment. So before that, we should have the calculations that if we transmit this power and if we encounter or consider these losses, all the losses that may occur in the channel, then what will be the power received by the receiver antenna? Then you will know that whether that power received by the receiving antenna is sufficient, whether it is greater than the minimum power or it is equal to minimum power or it is less than the minimum power. So if it is greater than the minimum power, then it's okay, no need to further improve on. If it is less than or equal to receiving a minimum power, then we either increase the transmitting power. That is a very basic way to adjust the losses, increase the transmitting power so that the received power can be increased, or we try to improve the channel quality by reducing the losses that the losses that we have in our hand, like filters and losses, transmission line losses, other losses that we can reduce. That, and then we can try to reduce the losses, or we will increase the transmitting power so that the receive power should be greater than the minimum power requirement of the receiving antenna. So let's see some classical propagation models. The average large scale path loss for an arbitrary long distance path loss model, the average large scale path loss for an arbitrary TR separation is PR at distance d is directly proportional to T over T naught powered by N. N is the path loss exponent or decay component that will vary from environment to environment. That is from rural to very densely populated urban areas. So N values vary or increases as we move from rural to dense urban. So it can be written in logarithm scale like this: PR d naught plus 10 n log d over d naught, where d is the distance where we would like to calculate this large scale path loss uh, receive power, and d naught is the reference distance up to where we know the power, and its values, the values of path loss exponent n depends on the specific propagation environment. We will see that in the next slide, and d naught must be chosen approximately so that the reference point is within far field of the transmitter. So for this you have to first calculate the far field and then keep the d naught within the far field distance. Like for large scale coverage, for large cellular coverage, d naught is usually 1 kilometer. For micro cell systems, d naught is usually in the order of meters. So see, free space n is equal to 2. For urban area and cellular radio, it is 2.7 to 3.5. Shadowed urban 3 to 5. In building line of sight 1 to 6, 1.8. Obstructed in building 4 to 6. Obstructed in factories 2.2 to 3. So see, the lowest value that we have is for free space, and the in building, if you are within the building, or we can have the micro cell, and we have line of sight, there is no obstruction in between the antenna and the transmitter, then it is from 1.6 to 1.8. For other environment, typically urban, shadowed urban, obstructed building and factories, a value of n is greater than 2. So larger value of n means we have the difficult environment, like we don't have line of sight, we don't have free space. So the n value of n should be as small as possible. That then you have the better receive power. So if n is greater, power reception will be affected. So then we have Okumura model, that is one of the most widely used models for signal propagation, signal prediction in urban areas, applicable for the following conditions. So this one again, Okumura model is an empirical model. Empirical model means it is tried and tested somewhere in the world in a particular setting. Like this Okumura name, Okumura is a name of scientist, and that scientist belongs to Japan, and he took experiments in the Tokyo, in the city of Japan, Tokyo, where he made all these experiments and used all these frequencies from 150 to 1920 megahertz, use these distances 1 kilometer to 100 kilometer, and different antenna heights from 30 meter to 1000 meter, and he like take the thousands of experiments, transmitting signal and then receiving. So he collected that data, and from that data he made an analytical expression that can be used to calculate the receive power somewhere else. But why it is called empirical? Because it is experimented somewhere else. But this can be applied model with some modifications, some tuning in other parts of the world as well. So this model is valid for these three conditions. The model provides a set of curves given the median attenuation relative to free space. Attenuation is an urban area over quasi smooth terrain with a base station antenna height 200 meter and mobile antenna height 2 meter, plotted over frequency 100 to 1920 megahertz. So this is the expression of this model that is derived or analyzed from the empirical experiments, where L50 is the median, 50 shows the average value of propagation loss, is the free space loss, LF plus are the losses that includes median attenuation, antenna height, gain of the antenna, transmitting antenna, and gain of the receiving antenna, and the total gain area. It is found that the antenna gain factors vary with respect to height as follows. So these are the expressions that you will use if we have different antenna and receiving heights. Other corrections taking into account important terrain parameters such as terrain undulation height, isolated ridge height, average terrain slope, mixed length C, parameter etc. are included as area correction factor as G area. So this one is your graph given by the Okumura, that is frequency against the attenuation. As you can see, as the frequency increases, attenuation also increases, and this correction factor for different frequencies and different environments, suburban area, quasi open area, and open area. So this factor should be used in accordance to this graph for different frequencies. So the model is wholly based on measured data and no analytical explanation is given. The simplest and best in terms of accuracy in path prediction for mature cellular and land mobile radio system is cluttered environments. It is standard for mobile system planning in Japan, not suitable for rural environment. Common standard deviation between predicted and measured path loss values are around 10 dB and 14 dB. So it is Okumura model is totally based on measured data. As I told you, experiments using experiment they measured data. No analytical, no formulas are used. From that data, they have given that expression, but using the mirroring the data, no expression has been, no analytical expressions, expressions or explanations given are used. The simplest and best in terms of accuracy in path prediction for mature is the cluttered. We have clusters, the cluttered environments other than the urban, other than the rural environment. It is for suburban, uh, suburban and urban environments, and common deviation is from 10 to 14 dB. Means value calculated using this model may vary up to plus minus 10 or plus minus up to plus minus 14 dB from the actual values. So that is the you can say the variance of this model. Then we have the Hata model. So it is again the empirical formulation of the Okumura model, valid from 150 megahertz to 1500 megahertz. So Okumura was from 150 to 1950. This one is from 150 to 1500 megahertz. And expiration is this one, where frequency is from 150 to 1500, transmitting antenna height, receiving antenna height. This one is the HRE. D is the TR separation, attenuation correction factor for effective mobile, and for a medium sized city, AHRE is given. So this one has better formulas than the, are more accurate than the Okumura model. Then we have small scale fading. Take a break of 5 minutes. We will continue after the break this small scale fading. So small scale fading or simply fading describes rapid fluctuations of amplitudes, phases, or multipath decays of radio signals over short period of time or travel distance. So the word is small scale fading. So fade means uh, reduction in something, like we say fade color means the color has reduced in its intensity. So this fading means reduction. So reduction in power, basically, that is what we are saying actually. So small scale fading means small scale power reduction. So why we say small scale? Because it is rapid fluctuation for small time. Scale here is for the time, small scale, small time, power reduction. So if you decode this small scale fading, this will be small time power reduction or power fading. If these are the rapid fluctuations in any of the characteristics of the signal, amplitude, phase, or multi-path decays of radio signals over short period, as I say, small time or of time or distance. Whereas the large scale path loss effects may be ignored. So large scale is from transmitter to receiver. Those effects are ignored when we consider only small scale fading. It is due to interference between two or more versions of transmitted signal arriving at transmitter at slightly different times, multi-path waves. So that is your large scale path loss. So the resultant signal varies widely in amplitude and phase depending on the distribution of the intensity and relative propagation time of the waves and bandwidth of the transmitted signal. So small scale fading or the fading phase can be categorized as follows. Rapid changes of signal strength over small distance or time, random frequency modulation, varying Doppler shifts or multi-path signals, time dispersion caused by multi-path propagation delays. So we divide the effect or the small scale fading into three. One is over distance or time. So rapid changes of signal strength. So these are the changes in the power, whether over the distance or whether the time. So those are your one category that we say rapid changes of signal strength. Second one is if the frequency is going to shift or change, so that we say the random frequency modulation, and that is due to the Doppler shift on the multi-path signals. Then we have the time dispersion, the time difference between the multi-path or the multiple signals of the copies of the same signal, and they arrive at different delays. So the time dispersion may accounted for the either uh, constructive addition or the destructive addition. In case of destructive addition, it's not good because it will interfere. The same copy of the signal may interfere with the original work. That is quite possible. So based on different parameters or factors, you can divide this small scale fading effects into different categories as mentioned here. In built-up urban areas, fading occurs due to lack of line of sight and line of sight path. Basically, this one is to lack of line of sight path and reflections from surrounding objects, example buildings. In the class I gave many times same example that we are sitting in the class, as at this time I am sitting in my office. Though I cannot see the transceiver or the base transceiver, base transmitter station, that is base station BTS, from my office. However, I am receiving signals on my mobile. So my mobile show me the strength of the received signals using the RSS. So that means the path between my mobile phone and the BTS from where I am being served don't have the direct line of sight path. So we are basically at non-line of sight path. So that is the prime reason of the small scale fadings, because the signal will reach to my mobile using the reflections. Reflection, maybe scattering, maybe diffraction, and other form of the physical attributes of the signals. So radio waves arrive at a different receiver from different directions with different propagation delays, with randomly distributed amplitudes, phase, and incidence angles. They combine vertically at the receiver antenna, so that may cause the fading or the reduction in the received signal. Even if the mobile is stationary, fading still occurs due to the movement of surrounding objects. If objects in the radio channel are stationary, fading is solely due to the motion of the mobile. The spatial fading is observed when a moving mobile is passing points with waves combining constructively and destructively. A fast-moving mobile may go through several fades within a short period of time. The mobile may also stop at a location with deep fade. So here it is like if you are moving too fast, then fading will be on the higher side, or there will be several fades occur within that time, or maybe a single deep fade or single drop in power. Single deep drop in power may cause the halting your connection, may drop the connection. Due to the relative motion between the base station and mobile, each multipath wave experiences an apparent shift in frequency. Then we know the Doppler shift if the relative motion between the base station and mobile is there, directly proportional to relative speed and direction of the mobile with respect to the base station. So it's very like the same way radar works. It works on this frequency shift. That is how we know that whether a target is moving towards us or moving away from us, because we can observe the shift in the frequency, and that shift in frequency is directly proportional to speed and direction of the mobile. Here it is mobile, in radar case it is the target. So that small scale fading with respect to frequency, that we say the Doppler shift, due to the Doppler shift, that is due to the speed and direction. Physical factor in radio channel that influence fading: multipath propagation due to reflection and scattering. Multipath versions of a transmitted signal arrive at the receiver displaced in time and spatial orientation. Random amplitude and phase of different multipath components causes fluctuation in signal strength at the receiver. Lengthens the time to send the baseband portion of the signal, that is RSI. So these are the factors that influence the small scale fading. Then we have speed of mobile. Relative motion between a mobile and a base station causes random frequency modulation due to different Doppler shifts on different multipath components. Doppler shift is positive and negative for a mobile moving toward or away from a base station respectively. That is, there is an increase in frequency, or the frequency will increase from its central frequency, that is Fc plus Doppler frequency, if a mobile is moving toward the base station at some speed, that is relative motion, and the frequency will reduce from the central frequency, that is Fc minus Doppler frequency, if a mobile is moving away from the base station at a relative speed. So it is base station and mobile is moving either towards the base station or away from the base station. Based on its movement, whether it is moving towards, its frequency will shift higher than the central frequency. If it is moving away, then its frequency will shift to lower frequency than the central frequency if it is moving away from the base station at a relative speed. If the surrounding objects are moving, they also induce time varying Doppler shift on multi-path components. Means if a signal is reflecting from an object that is moving, maybe a car that is a moving object, and if signal reflected from that moving object, that may be a car, and that car is moving at a relatively high speed, then that will induce time varying Doppler shift on the multi-path components. Time varying means it will have the different time dimensions than the other signals, and it will also experience the Doppler shift depending on the movement of the car, whether it's moving towards the base station or away. Their shift can be positive or negative. If their motion is greater than the mobile, the effect dominates the fading. Otherwise, the effect can be ignored and only the motion of mobile needs to be considered. Then we have very important factor, that is coherence time, that defines the staticness of the channel, is directly related to Doppler shift. So basically, coherence time is the time during which the signal will not change. It will be static for that time with respect to Doppler shift. Means in this time there will be no change or no shift in frequency, no time varying Doppler shift, no time dispersion and other things. So this is the time for which the channel remain static. Then we have bandwidth of transmitted signal. If transmitted signal bandwidth is greater than the bandwidth of multi-path channel, the received signal will be distorted, but the received signal strength will not fade much over a local area, fading not significant. So the bandwidth of the transmitted signal should be greater than the bandwidth of the multi-path channel. Then the fading will not be significant. Channel bandwidth is quantified by coherence bandwidth related to multi-path structure of the channel, a measure of the maximum frequency difference for which signals are still strongly correlated in amplitude. If transmitted signal bandwidth is less than the bandwidth of multi-path channel, then the received signal will not be distorted, but received signal strength will fade much over local area. Fading will be significant. Statistics of small scale signal strength and the likelihood of signal smearing over small scale distances are very much related to amplitudes and delays of the multi-path channel and the bandwidth of the transmitted signal. Coherence bandwidth is derived from RMS delay spread. That is a statistical measure of the range of frequencies over which the channel can be considered flat, past all spectral components with approximately equal gain and linear phase. The range of frequencies which two frequency components have strong potential for amplitude correlation. If the correlation is defined as above 0.9, then the coherence bandwidth is approximately 1 over 50 RMS delay spread. If the correlation is defined as above 0.5, then the coherence bandwidth is approximately 1 over 5 RMS delay spread. Now here is the word is flat. So flat means same for all frequencies. If the channel can be considered flat if all the frequencies pass through that channel, and all frequencies will undergo equal gain and linear phase, then that is your coherence bandwidth. So coherence time and coherence bandwidth are related to each other. We saw that coherence time is the time during the channel remain static, or at least we are saying now that it is a time during which channel will affect the all spectral components equally and approximately, means if the gain and phase of all frequencies change equally, then we say that channel is flat for a particular time, then it is coherence time, and the frequency that has passed will be termed as the coherence bandwidth. Now the range of frequencies which two frequency components have a strong potential or amplitude correlation. मतलब how much two frequencies are treated equally, how much they have the correlation, a strong potential for amplitude correlation. If that correlation between those two frequencies, between those range of frequencies is defined as above 0.9, but if the 90% of the frequencies in that range are correlated, then the coherence bandwidth more than 90%, then the coherence bandwidth expression is 1 over 50t. If the correlation is above 50%, then it is 1 divided by 5 coherence time. Sorry, RMS delay spread. Doppler spread and coherence time provide information about the time varying nature of the channel caused by the relative motion of the base station and mobile or and movement of objects in the channel. So I stop here. I have some other things, important things. I am in university, so I need some